How do you optimize heat dissipation in mechanical cooling systems? Imagine trying to keep a hot cup of coffee from spilling while walking on a bumpy road. That's similar to what cooling systems do. They keep heat steady despite challenging conditions. When designing cooling systems, the goal is to move heat away from components efficiently so they stay safe and work well longer. To do this, engineers focus on how heat moves through different materials and fluids. Heat mainly transfers through conduction, convection, and radiation. Conduction is how heat moves through solid parts, like metal heat sinks. Convection involves fluid flow, such as air or liquid coolant, carrying heat away. Radiation is less common but can be important at very high temperatures. Picking the right materials is key. Metals like copper and aluminum are popular because they conduct heat well. Copper is more expensive but transfers heat faster, while aluminum is lighter and cheaper. Sometimes, newer materials like graphene are used because they have even better thermal properties. The shape and layout of cooling channels also matter. For example, serpentine or multi-channel designs help fluids flow smoothly and remove heat evenly. These designs can be tested with computer simulations to find the best setup, reducing hot spots and keeping temperatures uniform. Thermal interface materials, or TIMs, fill tiny gaps between heat sources and heat sinks. Using thermal pastes or pads with high thermal conductivity helps transfer heat more effectively. Cooling can be passive, relying on natural convection and radiation, or active, which uses fans or pumps to circulate coolants. Liquid cooling systems are especially good for high heat loads because they transfer heat faster than air. To improve designs further, engineers use computer-aided engineering software to simulate heat flow and identify problem areas. Some even incorporate artificial intelligence to speed up the process and find better solutions faster. Multi-objective optimization helps balance heat removal, energy use, and temperature uniformity. For example, in electric vehicle batteries, optimized liquid cooling channels keep the batteries cool without wasting too much energy. In electronics, embedding cooling channels or vapor chambers spreads heat evenly and prevents hotspots. When designing cooling systems, it's important to consider the environment, fluid properties, and how the system will be used. Future innovations include new materials, nanotechnology, and artificial intelligence to make cooling even more efficient. Overall, making a cooling system work well involves understanding heat transfer, choosing the right materials, designing smart flow paths, and using advanced tools to refine the design. This way, systems stay safe, perform better, and last longer.